Welcome to this lesson 1.5 on atomic structure and electron configuration. So in this lesson, the main goal really is to revisit our understanding of what the atom looks like. Many of times we assume the Bohr model to be an accurate representation of what the atom looks like, but we're going to revisit the atomic structure and we're going to redefine how an atom looks like using electron configuration and the quantum mechanical model of the atom. So introduction here, atoms are made up from protons, which are positive, neutrons, neutral, and electrons, which are negative. The nucleus contains the protons and the neutrons while the electrons move around the nucleus. The majority of the mass of the atom comes from the protons and the neutrons, while most of the volume of an atom comes from the electrons. However, there is a great deal of unknown. In fact, our understanding of the Bohr's model of the atom with electrons traveling around in orbits has proven to be an incorrect model of what the atom actually looks like. In the quantum mechanical model of the atom, the electrons are defined by the solutions of a mathematical equation called Schrodinger's equation. Okay, now if you think about the quadratic equation that you may have studied in pre-calculus, the quadratic equation can give you 2, 1, or 0 solutions. So this equation, Schrodinger's equation, there are 4 possible solutions, and these are known as the 4 quantum numbers, represented by the variables n, l, m subscript l, and m subscript s. Okay, that describe the probable location of the electrons around the nucleus of an atom. Okay, so under this quantum mechanical model of the atom, all we can do is predict where these electrons might be, but we don't know for certain where it is. Okay, and so this mathematical equation that predicts the probability density, that is defined by kind of 4 variables here. Okay, so the first variable, n, this is what we call the principal quantum number, and this describes simply the distance from the nucleus. Okay, and so the values for n could be 1, 2, 3, 4, all the way to whatever n is. Okay, and this corresponds to the rows on the periodic table. Okay, so the first row elements there, so hydrogen and helium, they have kind of the principal quantum number of 1. Okay, so atoms kind of found in the second row would have a principal quantum number of 2 and so forth. The next variable, L, this is the angular quantum number, and this variable or this solution here describes the shape of the orbital. Okay, and so once again, orbitals, they're not just the racetracks that the electrons go around in the Bohr's model. Rather, these are 3D shapes, and we call them probability density that describes kind of where these electrons most likely would be. Okay, so the values for the angular quantum number starts from 0, goes 1, 2, and all the way up to kind of 1 less of whatever the principal quantum number is. Okay, and these solutions here, the 0, the 1, the 2, and the 3 for the angular quantum number, they kind of determine what type of orbital these electrons are going to occupy. Okay, so if you have a 0 for your L variable for the angular quantum number, that means you have an s orbital. 1 corresponds to a p orbital, D for or 2 for d orbital, and 3 for f orbitals. Okay, so right now we don't know too much what these orbitals are, other than the fact that, okay, electrons are occupying certain shapes, and we don't know where in these shapes these electrons are going to be, just that they're somewhere in those shapes. Okay, and these shapes are what we call orbitals. M with the subscript L, this is the magnetic quantum number, and this describes the orientation of the orbital, or in other words, kind of the direction these orbitals are facing. MS, this is the spin quantum number, okay, and this describes the spin of an electron. Okay, and there are 2 possible values, either a plus 1 over 2 or minus 1 over 2. And once again, these are just kind of the direction of the spin that we assign electrons. So either you have what we call kind of an up spin plus 1.5 or a down spin minus 1.5. Okay, so this is a simple kind of summary of what the quantum mechanical model of the atom is. Once you hit university or college, you do a lot more calculations using Schrodinger's equation, but we're just going to look at kind of the summary and the results of the Schrodinger's equation to try to understand what the atom looks like. Now, I keep talking about orbitals, or these shapes that electron occupy. Okay, so there are 4 different probability densities, cloud shapes, that describe the space that the electrons were most likely to occupy. And once again, we call these orbitals. Okay, they're described using 4 letters, SPDF. Okay, the S-shaped cloud or the S-shaped orbital is like a sphere around the nucleus. The P-shaped cloud looks like 2 balloons tied together. The D-shaped orbital looks like 4 balloons tied together. The F orbital looks like 6 balloons. Okay, so that's describing it. Now we have a picture here to kind of explain what all these balloons and spheres are talking about. Okay, so we can have an S orbital, and the S orbital, the S-shaped density clouds, usually this is just a sphere. Okay, so I'm just going to draw like a circle. Your P orbitals, okay, this is like 2 balloons or 2 lobes connected together. Okay, and the center dot here, that would be the nucleus. Okay, so same thing, the center dot here, this is the nucleus. Okay, so an s orbital is kind of like a spherical structure surrounding the nucleus. For the p orbitals, you have kind of 2 balloons tied to the nucleus, or 2 lobes. Okay, and for your d orbitals, if I have my nucleus, it's like having 4 lobes. Okay, for your f orbitals, this is like having 6 lobes. Okay, and what this means is that if I have an electron, the electrons could be anywhere in this lobe or in that lobe, anywhere. It could be close to the edge, could be close to the nucleus. We don't know, as that's the probability density of where the electrons could be. Okay, you'll notice that for your p, the d, and the f orbitals, there's multiple variations. Okay, so once again, even though I have a p orbital, I could have kind of multiple variants, okay, with different directions. Okay, and once again, the different directions, this is determined by your magnetic quantum number. Okay, so the m subscript L, okay, that determines kind of your different directions of the orbitals. Okay, so notice that for the s orbitals, there is only 1 variant. For the p orbitals, there's 3 different possible variants. For the d orbitals, 5. For the f orbitals, 7 different possible variants or different orientations. Okay, so the p orbitals can be arranged in 3 orientations around the nucleus. Okay, once again, d5, f7, and each orbital can fit 2 electrons. Okay, and each of them will have a different spin. Okay, so if I revisit my s orbital, I could have an electron here. Okay, and in the snapshot, I could also have an electron here. And once again, to kind of showcase that these are 2 different electrons, we assign them kind of the spin quantum number, so m subscript s. Okay, so this could be plus 1/2. This one here, this could be negative 1/2. Okay, just to differentiate that these are 2 different electrons. And same thing for my p orbitals. If I take a snapshot of the p orbital, I can have electron here, an electron down there as well. Just showcasing that, okay, at any given time, there are 2 electrons in this p orbital. I don't know where, but I know that they're going to be contained in that orbital. And so, we have all these orbitals with all these electrons in the orbitals. And so the atom is really just a series of orbitals overlapping other orbitals. Okay, so therefore one can imagine that the electrons are moving around in kind of a chaotic fashion around the nucleus. with certain areas that the electrons may frequent more than the others, once again, depending on the probability. Okay, so if you take a look at this atom diagram here, we have the nucleus, which is in the middle, and then we have all these orbitals just kind of overlapping, stacked on top of each other, right? We have some of these s orbitals, we have some p orbitals, and so the electrons could be kind of anywhere in these probability densities. Okay, once again, we don't know where exactly electrons are, just that it's contained in those shapes. Okay, so if we want to kind of distinguish these orbitals here, we're going to revisit kind of our principal quantum number n. Okay, so energy levels, these are the different distances from the nucleus. Okay, so that's what we call kind of the energy levels. So for example, I could have an s orbital with an energy level of 1. Okay, so notice how this s orbital is quite kind of close to the nucleus. At the same time, I could also have an s orbital with an energy level of 2, meaning that it's going to be a little bit bigger. Okay, or I can also have an s orbital at an energy level 3. Okay, so each energy level, there are different possible shapes or different shapes possible. So at the first energy level, the only orbitals that's available is the s orbital. Okay, so in that first energy level, I can only have the s orbital available. Each orbital can have 2 electrons. So in the first energy level, the maximum number of electrons is 2. Okay. At the second energy level, I can have an s orbital along with a p orbital. Okay, so s orbitals, there's one of them, I get 2 electrons. P orbitals, remember how there are 3 different variants? Okay, so if there are 3 different orientation variants of the p orbital, okay, times 2 electron each, that is 6. Okay, so I get a total of 8 possible electrons that can be in an energy level 2. For energy level 3, I have S available, my P's and my D's. Okay, so same thing, D. From the previous page, there are 5 possible variants. Okay, 2 electrons each, 10 total. Okay, and so 10 plus the 6 plus the 2, I can have 18 electrons occupying kind of energy level 3. Okay, and following the same pattern, energy level 4, okay, I can have 14 electrons. This comes from the 7 different types of f orbitals times 2 electrons each for 14, and that means I can have a maximum number of 32 electrons occupying that 4th energy level. Okay. Note that all these energy levels and orbitals are present for any given atom, okay, but based on the number of electrons that the atoms have, they may not occupy all these energy levels. So if I take a look at a hydrogen atom, okay, a hydrogen atom only has 1 electron, and so that 1 electron will be occupying energy level 1. Okay, if I have, let's say, a chlorine atom, okay, so chlorine atom here, assuming it's neutral, there are 17 electrons, which means that there's going to be some electrons in that first energy level, some in the second energy level, and some in the third energy level. Okay, and so I like to summarize all that numbers with a diagram here, and I like to use an analogy of a hotel room to describe this diagram. Okay, so at the very bottom of energy level 1, right, we only have the s orbital available. At energy level 2, we have our s and our p orbitals. At energy level 3, s, p, d. At energy level 4, s, p, d, and f. Okay, and so I like to use an analogy of a hotel room. Okay, so it's kind of like how, okay, on the first floor of the hotel room, I only have a single bedroom. Okay, on my second floor, I have single bedrooms. I also have double bedrooms. Okay, and on the third floor, I have my single bedrooms, my double bedrooms, and I have a king size bedrooms. Okay, and on the fourth floor, I have all the ones from before plus 2 king bedrooms. Okay, so Depending on the number of customers I get, right, I start filling them from the bottom. Okay, you are going to be taking these rooms, you're going to be taking those rooms. Okay, and so same thing for an atom here at the very bottom, energy level 1, there's only an s orbital available. At energy 2, there's the s and the 3 p's available. At energy 3, you have the s, the p's, and the d's. Energy level 4, s, p, d's, and f's. And depending on the number of electrons that you have, you would fill kind of this hotel or this energy diagram a little bit differently. Okay, so going back to my hydrogen example, if I only had one electron, okay, then that one electron is going to go at the very bottom here. Okay, and for electrons, we like to use kind of these half spins. Okay, so this is kind of an arrow pointing up, okay, and then this would be like an arrow pointing down. Okay, so for hydrogen, since there's only one electron, then I just have one electron occupying the lowest level energy 1 s orbital. Okay, if I had, let's say, a helium atom, okay, a helium atom has 2 electrons, okay, then I would have one for the first electron filled there, and then the second one sharing the room, okay, sharing the orbital. Okay, if I had, let's say, a carbon atom, no, let's do oxygen. Okay, so oxygen here having 8 electrons. Okay, then 2 electrons. The first electron will be filled here. The second one will be filled there. Okay, so that's 2 electrons filled. I still have 6 left. Okay, and so those 6 are going to be filling in the second energy level. Okay, so 1, 2, 3, 4, 5, 6. Okay, and so you'll notice that, okay, there's 2 of these orbitals that's unpaired. Okay, so these 2 orbitals here, okay, they only have 1 electron in the orbital. Okay, now if I go into another atom, let's say I have chlorine. Okay, so 17 electrons this time. Okay, so if I have 17 electrons, same thing, just like filling out the hotel. I start from the bottom. I have 1, 2, okay, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 4, 1, and 2 are all filled, but I still have 7 more electrons. So that goes 1, 2, 3, 4, okay, 5, 6, 7. Okay, so from this diagram here, we can see how, depending on the number of electrons, the number of energy levels and the orbitals that you occupy would be a little bit different. Okay, and so this is how different atoms differ from each other, because they're going to have a different energy diagram. Okay, now in reality, it's a little bit more complicated than just this. Okay, so in reality, each of these orbitals, they don't actually have the same exact energy. Okay, so for example, in energy level 2, the s and the p orbitals don't actually have the same energy. Rather, the p orbitals have a little bit more energy. Okay, and so this next diagram here is a better representation of the different energy levels. Okay, so for example, you'll see that this is the first energy level. This is like the second energy level. Okay, the third energy level is kind of like here, right? But because of the different amounts of energy that these orbitals have, okay, so you'll notice the 3Ds are a little bit higher, the 3S's are a little bit lower. Okay, and so it gets a lot more confusing because these orbitals start to overlap each other, right? If you look at kind of the 4s, you'll notice that the 4s orbital, because it has a lower energy, it's actually lower than the 3D. Okay, and so same thing, you have your 5s. This is actually kind of stacked in the middle of your energy level 4. So in reality, there's a lot of overlapping of these orbitals and energy levels. Okay, but the procedure to try to identify kind of each element is going to be the same. Okay, so for example, if I go back to the examples I was using, okay, if I have my hydrogen atom, right, hydrogen atom with 1 electron, okay, that first electron gets filled at the bottom. Okay, so we always start at the bottom. If I had my helium with 2 electrons, okay, so the first one gets filled there, second one gets filled there. Okay. If I then have my third example, which was oxygen with 8 electrons, okay, so the first, second, okay, third, okay, so notice this time I'm not going to fill the 2 p's yet because I'm going to fill the bottom from the lowest and up. Okay, so 1, 2, 3, 4, and then 5, 6, 7, 8. Okay, few general rule of thumbs. We always start from the bottom, okay, and we always fill every kind of orbital first before we start pairing them up. And if I go back to my chlorine example of 17 electrons, okay, so I have 17 to fill into my energy diagram or hotel for my analogy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, and so this energy diagram, that would be specific and unique to chlorines. Okay, so every kind of atom has its own energy diagram, okay, and how those electrons are filled in these orbitals. Quick kind of interlude here on Coulombs Law. Okay, so Coulomb's law here, force is directly proportional to the 2 charges and inversely proportional to the squared radius between these 2 charges. Okay, so the force will decrease the further away the particles are. Okay, higher charges, smaller distance between the charges result in a greater force of attraction. This explains why it takes more energy to remove electrons that are closest to the nucleus. Okay, in addition to the distance, the electrons that are on the valence shell, the outermost electrons, experience less of a nuclear pull because the electrons that are in the core of the atom block or shield the attraction of the nucleus from the valence electrons. And so these energy diagrams do a pretty good job of showing kind of what electrons are actually removed during ionization. Okay, so if I imagine that the nucleus is at the very bottom, then these 1s kind of orbital electrons, these are very close to the nucleus. Whereas these electrons here, these are further away from the nucleus. And so if you are ionizing kind of this atom here, if you're removing electrons, chances are you will be removing the electrons from the 3p orbitals first, okay, because they're further away, and because they're further away, the force of attraction is going to be a lot less. Whereas if you keep removing the electrons, if you keep removing, and when you're about to try to remove these electrons, okay, that is going to require a lot more energy because the distance between these electrons and the nucleus is a lot smaller. Okay, and according to Coulomb's law, that smaller distance results in a stronger force of attraction. Okay. Now, to represent or to draw these energy diagrams every time we talk about an atom is a painful process, right? So if I want to kind of show you what let's say iron is, the last thing I want to be doing is be drawing kind of, this huge diagram and filling in 26 electrons. Or if I'm looking at silver or gold, right, I don't want to be drawing all these diagrams and potentially up to 100 different arrows. And so there's an easy way to represent all this information, and that is called an electron configuration. And so an electron configuration, this type is a type of model of the atom that shows how the electrons are filled and in which orbitals. Okay, we call that subshell and energy level shells. Okay, so there's a few principles. The off-ball principle is to build up. Electrons are added to the lowest orbitals first and build up. And so that's why for these diagrams in my examples, I started from the bottom. Okay, you always start from the bottom and then you start to build your way up. You fill up. That's off-ball's principle. Hund's rule, each orbital should have 1 electron before any are doubled up, which is why when I was filling in these last electrons for chlorine. Okay, I put kind of 1 electron per orbital before I started to pair them up. And the third principle here, or the third rule, Pauli's exclusion principle, no 2 electrons can have the same set of 4 quantum numbers, which is why you'll notice that in our diagrams, we always have 1 upspin and 1 downspin. Okay, you are not allowed to have 2 up arrows in the same orbital. Okay, this is not allowed. Okay, so same thing when we're filling. Okay, you fill each of these orbitals before you start to pair them up. Okay, so you cannot start pairing them up right from the get-go. Okay, if they're of the same level, energy level orbitals, fill each one of them first and then pair them up. Okay. And so without drawing kind of the diagram, there's kind of a shortcut or easy way of trying to figure out what orbitals comes first and how many electrons you're going to be filling. Okay, so this is at the periodic table. It's the same periodic table that you've been looking at. Okay, but what's unique is if you look at kind of the labels here, for example, in the hydrogen, this is a 1s, helium 1s. If you look at kind of the second row, okay, so 3 and 4 lithium beryllium, these are kind of the 2s region. Na and magnesium, the 3s, the 4s, the 5s, the 6, the 7s. Okay, then you have on the other side, this is like what we call the p block of atoms, right? Because we have the 2p's, the 3p's, the 4p's, the 5p's, the 6p's. In the middle, we have what we call the d block. Okay, so these are kind of like my 3d, 4d, 5d, 6d. Okay, and inserted here, I have my f orbitals. I have my 4f and 5f. Another thing you'll notice that in the 2s region, okay, there's 2 elements there, 2 spaces, okay, corresponding to 2 possible electrons. If I look at my 2p region, notice that in this 2p row, I have boron, carbon, nitrogen, oxygen, fluorine, and neon, 6 elements corresponding to the 6 possible electrons. Okay, for the 3D, before even counting, right, we know that there are 5 orbitals, 2 electrons each, 10. Okay, so let's just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, in F's, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so it looks like that kind of the number of electrons per orbital matches up to the periodic table. Okay, so let's look at an example here. Find the electronic configuration of oxygen. Okay, so first thing we're going to do is we're going to find where oxygen is. Okay, so oxygen is right here. Okay, use the periodic table key as your guide. We're going to start at the beginning of the periodic table and write down the orbitals and the number of electrons as we move through the periodic table. Okay, so we're going to start here. Okay, and so the first orbitals I see are the 1s. Okay, now we're going to cross out kind of all the elements as we get to oxygen. So I crossed out one element of the 1s. I crossed out a second one. Okay, so since from the 1s I crossed out 2, that means I have a 1s2. Okay, so that means in my 1s orbital, okay, I have 2 electrons filled in. Next one here, I have my 2 s's. Okay, so that's the next orbital I see. Okay, and then I'm going to cross out both of these, meaning that there's 2 electrons in my 2s orbital. Okay, the next thing I have is 2p. Okay, and to get to oxygen, I'm going to cross out 1, 2, 3, 4. Okay, so that means of the p orbitals, even though I have a capacity to hold 6 electrons, I'm only occupying 4 electrons. Okay, so if I look at this diagram here, these 1s, 2s, 2p's, these are kind of what we call the orbitals or the subshells. Okay, I have a 1s2 at the very bottom. I have a 2s2 and a 2p4. Okay, and these numbers on the top, when we crossed out from the elements, these represents the number of electrons. Okay, and so let's double check. Oxygen, atomic number of 8, we know that it has 8 electrons. Okay, so those subscripts matched up, meaning that of those 8 electrons, 2 of them occupy the 1s orbital, 2 of them occupy the 2s orbital, and 4 of them will occupy the 2p orbitals. Okay, let's try another example. Let's look at neon. Okay, so same idea here. The first thing I'm going to do is I'm going to try to find where is neon. Okay, so neon is right here. Okay, so let's go through. The first orbital that I see is 1s. Okay, so both positions are going to be occupied, 1s2. The next one I see is the 2s. Okay, so I'm going to cross out these ones. So that's ns2. Then I have 2p, and let's see, to get to NE, I'm going to cross out 1, 2, 3, 4, 5, 6. Okay, so I'm crossing out all 6, 2p6. Double check. Okay, I have 2 plus 2 plus 6, that's 10 electrons, which matches that of neon. Okay, so instead of drawing these complicated looking energy diagrams every single time, okay, we can just use electronic configuration in the periodic table to figure out what's the unique identity of that element. Okay, so I just want to show you oxygen. So oxygen, we know it had 8 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. Right, so this is the 1s with 2 electrons. This is then 2s with 2 electrons, and then 2p with 4 electrons, okay, which matches the first example that we did. Okay, so instead of using a diagram, we can use the periodic table to help us figure things out. Okay. So this one here, once again, oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Okay, chlorine, which we did earlier. Okay, let's take a look at chlorine. So chlorine, this is 17 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, or if we look at the periodic table, chlorine, we can try to figure out the electronic configuration. Let's see if it matches that. Okay, so chlorine is right here. Okay, so I see a 1s, 2s, 2p, 3s, and 3p. Okay, so for chlorine, I see a 1s, 2s, 2p, 3s, 3 and p. Okay, and then let's see what we're crossing out. So I'm crossed out 1, 2. Okay, so that's 2. Okay, for the 2s, I crossed out 1, 2. 1, 2. For the 2p, I crossed out 1, 2, 3, 4, 5, 6. For the 3s, I cross out 1, 2. And for the 3p, I'm going to cross out 1, 2, 3, 4, 5. Okay, and this matches the orbital or energy diagram. Core notation. So once we're comfortable with kind of figuring out the electronic configuration for atoms, you'll notice that as you go further down the periodic table, your electronic configuration is going to get longer. And so there's a shortcut notation, and that's called core notation. And so core notation, it uses the core of an atom, which is a set of electrons with the configuration of the nearest noble gas, okay, to simplify the electronic configuration. Okay, so let's take a look at a few examples here. So I have aluminum, Al. Okay, now if I was to write out the entire electronic configuration, I have a 1s, 2, 2s, 2, 2p6, 3s1, 3p1. Okay, so it's not too long. But what core notation is you backtrack aluminum and you find the nearest noble gas. Okay, so aluminum is number 13 on the periodic table, but the nearest noble gas to it, right? So if aluminum is right here, Okay, you go backwards, and the nearest noble gas is going to be neon. And so what you can do then is in square brackets, put in Ne for neon. That represents that, okay, I'm going to go all the way to neon. And then once you have that, then you kind of start after neon. Okay, so then I have my 3s2 and then the 3p1. Okay, so that's kind of core notation where I can represent all this in the form of a noble gas. Okay, let's take a look at argon. Okay, so argon, this is going to be 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, so you're going to backtrack and look at the nearest noble gas. Okay, now you can't pick yourself. Okay, so argon can just pick itself. It still has to look back, and the closest noble gas is neon. Okay, so from neon, this is just going to be 3s2, 3p6. Okay, so go ahead and try Fe. Okay, so for iron here, once again, you look at the closest noble gas tracking backwards, that's argon. Okay, and then you look, okay, so I have 4s2, and this is going to be 3d, you count again, 1, 2, 3, 4, 5, 6, 3d, 6. Okay, oxygen 2 minus, chlorine minus, little typo there, aluminum 3 plus, calcium 2 plus. Okay, so anytime you have charges, if you have a negative charge, you're going to add electron. If you have a negative charge, you're going to remove an electron. Okay, so for oxygen, closest noble gas is helium. Okay, and this is going to be 2s2, 2p, usually 4, okay, but plus 2 electrons, 6. Chlorine, this is going to be neon, 3s, nope. 3s2, 3p, usually 5, but plus 1, 3p6. Okay, aluminum, you're going to remove electrons. Okay, so let's start off. This is going to be from neon. Okay, so usually this would be 3s2, 3p1. Okay, but you're removing electrons, so this is gone and these are gone. Okay, so you cannot just leave your answer as a noble gas. Okay, so you will always have to backtrack from it to figure out the noble gas before. Okay, you cannot quote a noble gas on its own. Okay, so we're going to then convert this, okay, back to He, and then this is going to be 2s2, 2p6. Okay, so for calcium, that would be the same thing. Okay, if we backtrack it, we would end up as argon, but we can't just put argon as its own. We can't quote the noble gas on its own. Okay, and so therefore we're going to use the one before, which is neon. And then continuing from there, this is going to be 3s2, 3p6. Okay, and so this is called electronic configuration, and it's a kind of a way to describe the energy diagram of electrons. Okay, because in the reality, or not in the reality, but in the quantum mechanic model of the atom, electrons are occupying these shapes called the orbitals. These orbitals overlap. Okay, and so, you know, the electrons are kind of chaotically moving around in their specified orbitals. We don't know exactly where they are, other than the fact that there's a high probability that they're, you know, within these orbitals. And that's kind of our current understanding of what an atom looks like. Okay, as always, please try the practice questions. Please try the fun sheets. Please email me if you have any questions or you see any typos. I'll see you all next time.